Today, we're diving into a battle that's happening on a microscopic level, but it has a massive impact on pretty much everything we build. It's all about the life and, well, the death of the cutting tools that shape our entire world. So, let me just start with a question for you. What is the one invisible enemy that every single engineer and machinist is constantly fighting? It's something that's always there, slowly destroying the very tools they need to do their jobs. And that enemy? It's wear. The slow, grinding, inevitable breakdown of the tools that cut, drill, and shape our modern lives. It's a constant war against friction and heat. So, how do we fight back? Well, let's open up the engineer's toolbox and see what we've got. All right, so this ongoing battle against wear is really at the heart of all manufacturing. If you can get a handle on it, you can make things better, faster, and a whole lot cheaper. But what exactly is tool wear when we get down to it? Okay, put simply, tool wear is just the gradual failure of a cutting tool. Every single time that tool slices through metal, the point of contact generates an incredible amount of heat and friction. And that constant stress just slowly but surely breaks the tool down. But here's the thing. Wear isn't just one single problem. It's more like a full-on assault from multiple directions. Think of them as the four horsemen of wear. You've got abrasion, which is basically like taking microscopic sandpaper to the tool. Then there's adhesion, where tiny bits of the metal you're cutting actually weld themselves onto the tool. Diffusion, where the intense heat literally causes atoms to flee from the tool's surface. And finally, delamination, where the tool's protective coating just gives up and peels away. So how in the world do you fight off all four of those horsemen? Well, your first line of defense is right there at the machine, the control panel. These are the key variables a machinist can tweak on the fly to manage the whole cutting process. And there are really three main levers you can pull here. Each one has a massive impact on how long a tool is going to last. We're talking about how fast you cut, how quickly you advance the tool, and of course, how deep of a slice you take. Let's start with cutting speed, because it's a perfect balancing act. Think of it like a car engine. You can cruise along at a nice low RPM, generating less heat, and the engine will last forever. Or you can redline it. You'll go a lot faster, boosting your productivity, but that intense heat you create at the tool's tip is going to cause wear to accelerate like crazy. It's always a trade-off. Now, you might think speed is the be-all and end-all, but that's not always true. A 2024 study on turning EN31 steel found something pretty surprising. The feed rate, that's how fast the tool advances into the material, was actually the single most influential factor. It accounted for over 60% of the difference in tool wear. It just goes to show you, sometimes how hard you push the tool can matter even more than how fast it spins. And that third lever, the depth of the cut, really acts like a force multiplier. While it might be a secondary factor a lot of the time, taking a deeper cut dramatically increases the physical stress on the tool. You can think of it as just amplifying all the damaging effects of both your speed and your feed rate. Okay, so we've seen how adjusting the process itself can help. But since so much of this wear is driven by just extreme heat, the next logical step is to try and control the environment. It's time to figure out how to beat the heat. On one end of the spectrum, you could just do dry machining. It's cheap, sure, because you're not using any coolant, but the friction and heat are intense, and you get severe tool wear. But on the other hand, you have cool techniques like minimum quantity lubrication, or MQL. This sprays just a tiny targeted mist of oil right where it's needed, and that little bit is enough to slash friction and heat, and studies show it can make a tool last significantly longer. But what if you need to get really extreme? I mean, what if you need to take cooling to a whole other level? Well, that's where cryogenic cooling comes in. We're talking about using things like liquid nitrogen to basically flash freeze the cutting zone. This isn't just making things a little cooler. It's fundamentally changing the entire thermal environment of the cut. And the results? They can be absolutely astounding. A 2025 study looking at machining really tough SS316 steel found that going cryogenic was superior across the board. It didn't just reduce wear, it actually lowered the amount of physical force needed to even make the cut in the first place. So we've controlled the process, we've controlled the environment. What's next? Now we turn our attention to the tool itself, to its basic makeup and the protective armor it wears into battle. You know, this is really a fundamental truth in manufacturing. You can have the most perfect process in the world, but if your tool's material isn't up to snuff, it's going to fail, period. This is where material science becomes your ultimate line of defense against wear.
And modern cutting tools are rarely made of just one thing. They often wear what you could call a suit of armor, these specialized coatings designed for very specific jobs. For instance, studies show AL-CRN coatings give you superior wear resistance in general. But if you're trying to cut something incredibly hard, like hardened steel, you'd switch to something like PCBN, which absolutely excels in those high-stress situations.
So how thick is this game-changing armor we're talking about? Get this, research shows that for some of these advanced nano coatings, the sweet spot is just 5 to 8 micrometers thick. To put that in perspective for you, that is way thinner than a single strand of human hair. And yet, that microscopic layer is the only thing standing between the tool and total destruction. All right, we've made it to our final weapon in the fight against wear. And it might be the most subtle, but it's also one of the most critical, the actual shape of the tool itself. And this is so important to grasp. The angles, the curves, the edges of a cutting tool, none of that is an accident. Every single feature is meticulously engineered to manage forces, to control how the material flows as it's being cut, and ultimately to resist wear. Just look at the difference it makes. If your geometry is off, things like your key rake and clearance angles, you can end up concentrating all of that cutting stress onto one tiny vulnerable point. That creates massive friction and causes the side of the tool to wear out incredibly fast. But with optimized angles, that very same stress gets distributed much more evenly. The chip, that little sliver of metal being cut away, flows smoothly, which dramatically reduces wear and extends the tool's life. And all of this leaves us with one final, pretty fascinating question. This whole battle we've been talking about, balancing speed, temperature, materials, geometry, it's all a response to the materials we're trying to cut today. But as we keep inventing stronger, lighter, more complex materials for things like spacecraft and medical implants, what will the tools of tomorrow even look like? The fight against wear, you see, is never really over.